Hi everybody, welcome back. Today we're going to review graphing exponential functions, and we'll go through quite a few examples. So before we start graphing, let's review what the general exponent rules are. If you have a base, let's say a base of 2, and we raise that to the 0 power, that's always going to equal 1, right? Anything raised to the 0 power equals 1. And of course, anything raised to the power of 1 is itself. It's going to always equal the base. Do you remember what happens when you have a negative exponent? You get the reciprocal. And of course, we know 2 to the negative 2 would be 1/4. 2 squared is just 4. So if we use these observations with just the basic rules of exponents, it makes it a lot easier when we start graphing exponential functions, especially when we don't have a calculator. So when we start graphing exponential functions, it's always easy to put in the value of x equals 0, because in your exponential function, the variable x is your exponent. The format of an exponential function is a times b, which is the base, raised to your variable x minus h, that's your horizontal shift, and then plus k, that's your vertical shift. The a, just like in all of our other functions, that's the stretch factor. And if it's negative, it'll reflect over the x-axis. The h, that's your horizontal shift. And the k, that's your vertical shift. So if we go back and we use these exponent rules, and then we try to incorporate those when we're graphing an exponential function, they're really pretty easy functions to graph. So grab a piece of paper and let's go through a bunch of problems together. So let's try these problems. Let's see if we can graph these. So if we look at number 1, this is going to be one of the most basic exponential functions. We have, on number 1, we have a base of 2, and this function isn't being shifted left or right, it just occurs at the origin. So let's try that and see where we go. So I'm going to think about what my values are when I have 2 and I raise it to various exponents. So in an exponential function, the variable x is my exponent. So when I try different values of x, that's how I'm going to get my coordinate points. So I'm always going to start with, I'm going to give myself a little space here, but I always want to think about when x equals 0, because we just said earlier that when x equals 0, to get my y value, I would just say 2 raised to the 0 power, that's 1. So let's go ahead and plot that. So I have 0, 1. Well, so what happens when I have x equals 1? Well, that's just 2 raised to the first power, so I get 2. So 1, 2. And when I have x is equal to 2, that's going to be 2 squared is 4. 2, 4. And then what happens when x is negative? Well, when x is negative 1, I get 2 to the negative 1. That's just 1/2. And so I'm just going to kind of guess there. And if I had negative 2, that would be 2 raised to the negative 2. That's 1/4. And with exponential functions, we're going to have an asymptote here. And that's a line that the function will never cross. And in this case, y can never equal 0 in this function, because no matter what negative exponent I put in for x, I can never get it to decrease to 0. So it's going to get really close to 0, but never quite get there. And of course, as x gets bigger, y is going to increase as well. So I'm going to highlight the asymptote here with yellow highlighter. And so I have my asymptote is y equals 0. So if I can plot those points, we just plotted 5 points really quickly without a calculator. It's really easy. So if I have to describe the graph for a typical exponential function, my domain is always going to be all real numbers, because I can put in any value for x. There are no restrictions there. But the range, we know the graph will not go to 0 or below. So it gets almost to 0, but not quite. So I'm going to use an open bracket and then unlimited values of y in the positive direction. We also might need to identify where the function is increasing. So in this case, remember when we're talking about increasing or decreasing, you always want to start at the low values of x, like down here. Pretend you're the little bug on the graph and you're going from the left toward the right. So as x gets bigger, what happens to y? Well, in this case, it's getting slightly bigger, slightly bigger, slightly bigger. And then of course it's continuing to increase up here. So the graph is actually increasing for all possible values. So it's all real numbers. And then where is it decreasing? It's not decreasing anywhere. So we would just say none. Then for our x-intercept, remember your x-intercept is where y equals 0. So where it crosses the x-axis. Our graph doesn't cross the x-axis, so we don't have an x-intercept in this case. What about the y-intercept? The y-intercept is when x equals 0. So we know that that's at the point 0, 1. And then the last two features, where is the graph positive and where is the graph negative? So the graph is positive. What that means is where y is greater than 0. And in this case, everywhere that the graph exists, it's positive. So that's going to be all real numbers. And where is it negative? Negative would be down here. That's where y is less than 0. But because of our asymptote here, we know that y will never be negative. So in this case, the answer for that is just none. Okay, so that's probably the most basic exponential function we can have. So if we go back to the format of our exponential function, now if we start to incorporate other things into it, like a stretch factor, a negative value of a horizontal shift and a vertical shift, let's look at how those different things can influence our parent graph. So I'm going to call the graph we just did our parent graph. And so now if I go back and look at the problems we're going to try to do, if 1, this is my parent graph for anything that has a base of 2. So if I look at that and I look at the next couple problems here, well, what's happening? Well, on number 2 here, this is just going to have a vertical shift. So this will be my parent graph shifted down 3 spaces. And if I look at number 3, this shift is in the exponent itself. So when you look at your exponents, think of that part being written in parentheses like I just added there. And remember, I want to go the opposite way of what the sign is. So in this case, I'm going to shift my parent graph left 1 space. And then problem number 4, that's incorporating a vertical shift and a horizontal shift. So this one's going to shift left 1 and up 3. So all of these functions are using the parent graph so I can look at my parent graph of 2 to the x and then just shift those points around based on whether it's a vertical shift or a horizontal shift in this case. So let's try those and then we'll come back to 5, 6, and 7. Because 5, you'll see that's also a parent graph, but this number 5 has a base of 3. So let's go look at the parent graph transformations for problems 1 through 4 and see what happens there. Okay. This shift, the 2x minus 3, we already said that that's going to take my parent graph and shift the points down 3 points. So if you look here, we've plotted the points for our parent graph. So let's see these. Those are the points that we had on our parent graph that we just did. And now I'm just going to count down 3 spaces. So when I start with my point of 0, 1, like I had on my parent graph, I count down 3 spaces. And I end up with 0, -2. And then if I go to the green point, which was on my parent graph, it was 1, 2. If I say 2 minus 3, I'm going to get my point 1, -1 right here. And if I go on to x equals 2, my parent graph, if you remember, 2 squared was 4. And now I just say 2 squared is 4. 4 minus 3 is 1. And so I can shift my entire graph down that way. Now, other things are going to change as well because now I've also adjusted the asymptote. So what's the asymptote now? That's right, -3. So since I adjusted the whole graph down by 3, that's going to shift the asymptote. It's also going to shift the y-intercept and the x-intercept. So if I look at my graph, my domain, still all real numbers. My range now, instead of going from 0 to infinity, it's going to start at -3 and go on to infinity. The graph is increasing, still everywhere because I haven't flipped it upside down. And it's still not decreasing anywhere. Right? And so then I had my x-intercept. If you remember on my parent graph, the x-intercept was none because it didn't cross the x-axis. Now my x-intercept is going to be right here somewhere. And we actually don't know how to find that yet. When we get to logs, we'll be able to find the actual x-intercept. So just realize that there is an x-intercept here at this point. And of course, the way we would find that is we would set our equation equal to 0 and solve for x. But we don't know how to get rid of this exponent yet because we haven't covered logs. Once we have logs, we'll be able to do that. So at this point, we just want to know there is an x-intercept. For the y-intercept, that's where x equals 0. And in this case, when x equals 0, y equals -2. And then now what about the positive and the negative? Well, the graph is positive all in here. So we want to clarify the range of values that make y positive. So the positive values would go from the x-intercept to infinity, and the negative values will go from -infinity up until the x-intercept. And so for this unit, when we don't know how to use logs to solve for x, you might be given a problem on a test where they actually identify what that point is, and then you would have to fill in the value here and here. And just know that the positive values and the negative values are influenced by the x-intercept. But as far as graphing goes, it's really pretty straightforward. So now pause the video and try 3 and 4 on your own. Then come back and check your answer. Okay, here's number 3. We just shifted everything left one space. And then when we adjust the characteristics, notice that the y-intercept changes, but everything else stayed the same as our parent graph. Okay, so let's go do our last problem, number 4. Remember that we were going to adjust our parent graph left 1 and up 3. So after we do that, note that that changes our asymptote, which is now y equals 3. And so that changes the range and the y-intercept. But everything else remains the same as our parent graph. I'm hoping that helps give you a good review of graphing exponential functions. And we covered the vertical and horizontal shifts today. I'm going to save the stretches for another video so it doesn't get too long. Thanks so much for watching. Have a great day.